You've probably seen it before. You type an address into a website and boom, it spits out a home value. It feels like magic, right? Well, it's not magic, it's machine learning. And today we're going to pull back the curtain and see exactly how machines learn to predict the price of, well, just about anything. So let's start with this house. How much do you think it's worth? It's a tricky question. You've got to think about the square footage, the neighborhood, the number of bedrooms, maybe even the age of the roof. How on earth can a computer take all those little details and boil them down into one single accurate number? Because they can, and they do it in an instant. But the real question, the one we're diving into, is how do they learn to do that? They aren't just programmed with a bunch of rules. They actually learn from data. So let's explore how that learning process actually works. Now, in machine learning, there are different kinds of predictions. Predicting if an email is spam or not spam is one thing. That's like sorting things into two buckets. But predicting a price, that's a whole different ballgame. The answer could be any number along a continuous line, which makes it a lot tougher. The tool for this job is called regression analysis. It's a bit of a fancy name, but all it really means is finding the relationship between different pieces of information to predict a number. You know, things like stock prices, the temperature tomorrow, and, yep, you guessed it, house prices. To really get our hands dirty, we're going to become data detectives. And our case file is the Ames Housing Dataset. It's packed with real information on houses sold in Ames, Iowa. Our mission is to sift through this data and build a model that can guess the sale price of a house it's never seen before. Okay, let's take a peek inside the file. You can see we've got columns like ground living area and overall quality. In our world, we call these features. They're the clues. And then there's the sale price. That's our target variable. It's the answer to the mystery we're trying to solve. The whole game is about figuring out which clues are most connected to the final answer. Now, you don't just jump in and start building. The first thing any good data detective does is something called exploratory data analysis, or EDA for short. This is where you just look around. You're searching for patterns, for hints, for the strongest clues that will lead you to the solution. And we have a couple of go-to tools in our detective kit. The first is a scatterplot matrix, which lets us literally see how different features relate to each other. The second is a correlation matrix, which gives us the cold, hard numbers to back it up and tell us just how strong those relationships are. And bingo! We've got our first major lead. The correlation between the ground living area and the sale price is a massive 0.71. That's a really strong signal. It tells us in no uncertain terms that as the size of a house goes up, the price tends to go up too. This is the perfect place to start building our model. All right, now that we've got our strongest clue, we can build our first model. We're going to start with a classic, super powerful technique called simple linear regression. So imagine you plotted every single house from our data set on a graph. Along the bottom, you have the living area, and up the side, you have the price. You'd get a big cloud of dots. The whole goal of simple linear regression is to draw one single straight line that slices right through the middle of that cloud of dots in the best way possible. Now, don't let the equation on screen scare you. It's just the recipe for a straight line. You probably remember something like y equals mx plus b from algebra class. It's the exact same idea. The model's job is to figure out the two magic numbers, w0 and w1, that define the perfect starting point for the line and the perfect slope or steepness. Of course, that line isn't going to hit every single dot perfectly. For each house, the distance between the actual price, the dot, and our line's prediction is called the residual. You can think of it as the error for that one prediction. And the goal of our model is to find the line that makes those errors, when you add them all up, as tiny as possible. So we have a model, we drew our line, but is it any good? How do we actually grade its performance? I mean, how do we know if our guess is a good guess or a terrible one? For that, we need some scoring metrics. We've got two main ways to do that. The first is mean squared error, or MSE. It basically measures the average size of our mistakes. So for MSE, lower is always better. Then there's R squared. This one's a little more intuitive. It tells us what percentage of the price variation our model can actually explain. For R squared, you want a number as close to 1 as possible. Now, a straight line is a great start, but real-world data is messy. It's never that clean. You'll always have outliers, those weird data points that just don't fit in. And sometimes the relationship between two things just isn't a straight line to begin with, so we need some fancier tools. One really clever way to deal with outliers is an algorithm called RANSAC. It's short for Random Sample Consensus.
Here's how it works. First, it just grabs a random little group of data points it thinks are normal. It fits a model to just them. Then, it checks all the other points, and if any of them fit that model pretty well, it adds them to the good group. Finally, it retrains the model on this new, bigger, cleaner group, basically ignoring the weirdos. Pretty smart, huh?
And what about when the pattern isn't a straight line? Well, for that, we can use polynomial regression. This technique lets our model fit curves instead of straight lines. We do this by adding new features like the living area squared. This gives our model the flexibility it needs to bend and follow more complex patterns in the data. Okay, so we've been focused on drawing one single line through our data, whether it's straight or curvy. But what if there's a better way? What if we've been thinking about this problem from the wrong angle? Let's check out a totally different approach that's often way more powerful. Instead of one big formula, a decision tree works by asking a series of simple if-then questions. It's like a flowchart. It might ask, is the living area bigger than 1,500 square feet? Yes or no? Based on that answer, it goes down a different branch and asks another question. It keeps splitting the data like this until it gets to a final price prediction. It thinks in steps, not smooth lines. Now, a single decision tree can be powerful, but it can also get a little obsessed with the training data and not work so well on new stuff. So what's better than one tree? A whole forest of them. A random forest is just a collection of many different decision trees. It builds a bunch of them, each one slightly different, and then it averages their predictions. It's like asking a committee of experts for their opinion. And this is why data scientists absolutely love random forests. They aren't easily thrown off by outliers, they work incredibly well with very little tweaking, and they're much more stable than a single tree. And maybe best of all, they can actually tell us which of our original clues, which features, were the most important for making the final prediction. Which brings us to the big reveal. After all that work, our random forest model tells us exactly what mattered most. And look at that. The number one most important feature for predicting a house price was overall quality. That was even more important than the grounds living area or the total basement square footage. This is what it's all about, using these tools to find the real story hidden in the data. So we figured out how a machine learns to price a home. But the really cool thing is, you can apply these same ideas, finding clues, fitting a model, using a whole forest of them, to predict almost any number you can think of. It makes you wonder, right? What other complex numbers out there are just waiting to be figured out if only we ask the right questions? Thanks for joining me on this one.